Hi, everybody. I think we are live now. I hope everyone can hear me well. Welcome to another member of community call. I'm Mata from the Developer Experience team here in Memgraph, and today with me I have Frank Blau. I'm hoping I pronounced that right, who is a principal data engineer. And today we're going to demonstrate the real-world challenges of helping developers shift from relational models to the graph-based thinking. So as a graph database, we often get a bunch of questions from our developers who are either currently migrating from a relational database, they're thinking about migrating, but they're not sure if their use case is suited for a graph, or maybe they just had an aha moment of like, oh, my data would make much more sense as a graph. So I'm really looking forward to this talk and to hear what Frank has to say today to us. So before we begin, just a small note that we have a chat here, so feel free to ask any questions to Frank, either here or in the Q&A section, and then Frank will answer those questions at the end of the presentation. And we also have few polls posted, so feel free to cast your vote there as well. So yeah, that's it for the intro. That's it from me. I'm now going to step back and let Frank take.
Thank you so much, Matea. I'm really happy to be here today because this is a topic I have been talking about for a long time. And not just actually relational to graph, because that, if you've been around the world of databases, I think you know relational to graph is kind of a leap over a lot of other things also, like document databases and time series databases and data warehouses and a bunch of other different architectures. But this world of how we get from one architecture to another and how we can communicate with people who are either want to get there or are there and confused or just interested in the topic is something I've made a lot of my presentations about. And so I'll send some links later to some other sort of maybe a little more esoteric in places, but topics similar to this one about how you choose data architectures and things like that. So, but I'm going to start my presentation here. Let me just share my, oh, that's the wrong share. Hold on just one second. There we go. Screen. I actually have to share a whole screen here. One second here. Window. There we go. Okay. So if I switch this to, how's that look?
Great.
Super. Okay. So I decided to call this "Where Are the Tables?" is because that's a question I get actually when I suggest graph architecture a lot of the time. People are like, okay, I think I see the pictures that you're drawing, but I don't really know, I can't relate this to the way I think about data. And if you think about where graph databases started, if anybody have been around them for a while, for a lot of time, a lot of the history of graphs and the sort of similar kind of structures, it was very difficult to have this conversation because you couldn't map the way they saw the data world to the way graph saw the world. And so this question, where are the tables? Where is the data? Where are my attributes? Things like that were questions I used to get all the time. And like I said, I'm not going to go into all the different architectures. We're going to kind of just stick with relational and graph, but a lot of these conversations do apply to other data architectures also. The first thing I want to say is that there is this idea of a relational mindset. That is, we think of things in terms of tables and rows and columns and the relationships between them and how we connect them. These are kind of the core elements of a relational database that anybody who's doing anything with relational databases probably knows these things already and knows how to work with them. And they're the ones who sometimes have the difficulty mapping what we think about in a graph mindset, which I'll talk about in a second. But for those of you who might not have some of this undercurrent of relational, is we put data into tables of related information, and those tables have rows, that is records, and columns, which are their attributes. And you can tell I lived in Italy because I talk with my hands all the time. Um, and then when we want to make a relationship between two tables, we create a foreign key and a primary key relationship between them. That is, if I have a customer in one table, I can show you here, you have a customer in one table and a customer has many orders. So we put the customer ID in the order table. It's called the foreign key here. And we can say one customer has many orders. And I'm purposely doing this very simply right now because relational databases can get very, very complex. If you've ever dealt with anything like SAP or any large ERP system, they can have thousands of tables in some cases with cryptic names and cryptic column names and a bunch of really strange stuff going on. But when we started building more intelligent systems, and we wanted to build data warehouses, for example, where people can get an analytic perspective of their data, oftentimes what I would do is I'd be in front of a whiteboard with my subject matter experts in the room, and I'd be drawing circles and lines. I would be drawing things like, oh, the product is purchased in an order. A person knows about a product. A person purchased an order. And I would draw these things on the board with lines and circles. And then, being a consultant, I would get paid to go out and build this model from this drawing. But in a graph, these things are your model. And that's a really powerful way of understanding data. You don't have to go through this huge translation layer of what is a graph towards what am I actually going to deliver at the end of the day. The graph is your model. And that's something that really sets graph apart, in particular, when we start assigning attributes to the graph. And something where we can say, hey, where are your tables? And I'm going to show you some examples of that. And what can I do with them that I'm used to doing in my relational context? So the graph mindset is a little bit different. In the graph mindset, we break the world out into nodes, that is, entities, and their properties, which is attributes. So you can think of a node sort of as like a table of stuff, and the properties associated with them. And then the relationships are just those connections between them. But this slight difference here in that when I was talking about the relational database, you notice I say this is a one-to-many relationship between customer and customer, the orders that they place. If I look at this in a relational database, that is all I know about that relationship. There's one of these and there's many of these. Whereas in a graph model, I say the name of the relationship tells me something important about it. This is a product was purchased in an order. A customer placed an order. A customer purchased an order. It's a little bit strange terminology in this example. And you get this richness of models that is really valuable because the relationship itself, I like to say, the relationship itself becomes a first-class citizen on your data network. And that is something that is very challenging to do sometimes in a relational database. Ironically, it's a relational database. You would think the relations would be the first-class citizen, but they're really not. Now, you can model things into a relational database that allow you to talk a lot more about what the relationship means, but they tend to be schemas. They tend to be more tables. They tend to be more attributes, and you have to maintain them, and they're not very flexible. Unless you are a super clever developer, a relationship is what it is. Whereas in graph, I can have all sorts of ad hoc relationships. I can create multiple relationships between entities, all with this rich semantic ability to describe exactly what is happening in the data in my graph. And that's something that I really like about working with graphs. So we have these two different mindsets, the graph mindset and the relational mindset. This is an example of what we call an ER, an entity relationship diagram. It's kind of how we draw models of things in a relational database. So let's go back here for a second. In this example, what I'm representing is a one-to-many relationship. How do we do that in a graph? Well, in a graph, one-to-many is just a relationship between the things. So I have a department here, and a department here. And Alice, who belongs to 3 different departments, maybe she's a professor and she teaches in 3 different departments, she belongs to this one, she belongs to this one, and she belongs to this one. A one-to-many relationship. And the labels of that relationship tell us something about it, right? And the nice thing about graph is I can sort of, if I look at this, okay, I'm a smart guy. I can look at this and kind of figure out what it's doing, but I may not know if I'm using an ERP system, for example, where they don't use such friendly names as customers and orders and IDs and things like that. It's sometimes very difficult, or at least it takes some time to understand what the model is supposed to be doing in a relational database. Whereas in a graph, you just sort of have to look at it and read through the semantics of it. Alice belongs to this department. Alice also belongs to this department. These are the nodes, and these are the relationships between them. And the ability to sort of read this makes it really easy as a consultant or as an analyst to have conversations with people about what I'm talking about. Instead of saying, okay, you've told me all this stuff, I'm going to go away and build a model that you're not going to understand, but it's going to do everything you want, right? And then we want to go back and talk about it again. It can get very complicated. When I was first starting my consulting career, I would always at least try and teach my customers a little bit about data modeling first, so we could at least be speaking the same language, like one-to-many. I would tell my customer, ask my customer, is that a one-to-many relationship? Is it a one-to-one relationship? Is it a many-to-many relationship? And those things, in my mind, when they would have these conversations, I would draw things like this on the board. And then I would say, okay, in my head, I'm going, okay, I know how to model that, put that in a box, put that in a box. But there was not this one-to-one relationship between them. Now, I just mentioned something about a many-to-many relationship, which is another type of SQL table architecture that we create. An example of this is, and the funny thing is the example I'm using here, books and authors, is one of like the oldest examples in the database world. I think it used to be called the Northwind database, something like that. I forget. It was an old a Microsoft database. But in this example, books and authors are 2 different tables, but the relationship in them is many books are written by many authors, and some books have multiple authors. Some books only have 1, some may have 2, and they may have different kinds of relationships. Someone may be an editor of the book. They may have different kinds of relationships through different people. So this is that sort of fixed world of how we model many-to-many relationships in SQL. And we call this table in the middle here, this is books, this is authors, and we call this table in the middle a resolver table. And it resolves the relationship between this one-to-many relationship and this one-to-many relationship, which if I have 2 of them, it becomes a many-to-many relationship. I hope most of you are sort of at least somewhat familiar with this. If you're not, just ping me, happy to explain it anytime. So how do we do this in a graph? Well, in a graph, many-to-many relationships are just more edges, right? So if I have, for example, J.R.R. Tolkien is the lead author on Lord of the Rings, but Neil Gaiman is a co-author of, what is he a co-author of? American Gods. Right? Or maybe he's the lead author, and I can't quite see it in this case. Or Stephen King may be a contributor to Good Omens, and Terry Pratchett is the co-author. And these all can represent many-to-many relationships in a graph. And you can query it that way. You can do all of this stuff that you want to do with a many-to-many relationship, which is, for example, show me all the books and who their authors and co-authors are, but show me the relationship also. Like, is it an author? Are they the co-author? Are they the editor? And the relationships, as you can see from looking at this example, get elevated to being very important parts of your data architecture that are semantically called out and specified in a very specific way so that you can use them in your queries. And we're going to see some examples of this in my code a little bit later on, assuming my demo works perfectly, which of course it will. But I want to talk about one more type of data architecture that is interesting to me. And I always, whenever I would look at a new database tool or a new modeling tool, I would always throw this at it. And this is what we call a slowly changing dimension. And this is a concept in data warehousing where we say, hey, Ricky Green exists in my source system, but Ricky Green changed his name to Ricky L. Green. But I still want to remember that he was called Ricky Green at some point also. Maybe it's a sports app or an authentication app or something like that. And so when I create my reporting database, which is the lower box you see here, I say, well, the first time he came through, he was Ricky Green. So he got his ID, his source system ID is 2, which it matches up above. But when he came through the second time, he had a different name. So I create a different row for him. It's still the same source system ID, but I have a different surrogate key. So I can attach, for example, events of different types to him. So one example that I give of this doesn't really show it that well. I probably could have edited this to show it a little bit better. They call it the beer versus diapers. Like, what do single people buy versus married people buy? And if all I have is this top table here, let's say I'm looking at Jane Doe and she's single and she purchases some stuff, and then I update her record to married, and then she purchases some more stuff. Can I differentiate between the things she purchased as a single person and the things she purchased as a married person? If this is the only data I have, this top table, I can't do that. But if I've implemented this, what we call a slowly changing dimension strategy, I can actually do that in my data. This is a sort of a complex data warehousing topic, and a lot of my conversations with customers over the years have been around this topic. What are your slowly changing dimensions? Why is this attribute changing important to you analytically? And we would model the systems to do it. But the ETL, that is the extract and transform and load software that we use to build these slowly changing dimensions, has to take into account some very sophisticated SQL sometimes. If multiple things can change, for example, which one represents the change? Do I take a separate record for all of them? Do I include all of them in one batch? All of these are questions that go to your analytic architecture. Well, in a graph, interestingly enough, it's actually pretty simple, because I can have all of these relationships, and they can have, for example, different dates associated with them. So if I'm in this postal code in a certain date range, and then I'm in this postal code in another date range, I can actually just create different relationships. Or I could have it all inside of one relationship and different attributes, like an array of attributes, to represent the changes between them. All of these things represent data architectures that we have in complex SQL situations, that is, in the tables, to moving it to a graph where we can actually look at it in a different way. Now, when I first started modeling these slowly changing dimensions in graphs, I have to tell you, it was sometimes very difficult to communicate with people, particularly data analysts, other data architects, about what was valuable about doing it in a graph. Why not just do it in SQL? Well, I've made up a list of things here that make it a little bit easier to understand why the graph is advantageous in this case. For example, in my relational database, the relationship between things doesn't have any values. It's just the cardinality, one to many to many, like I discussed earlier. But in a graph database, it can have temporal properties. When's it valid from? When's it valid to? Is this the current record or not? And that is an attribute of the relationship that I don't have to put in the node itself. I can make that an attribute of the relationship itself. And so it's really easy to do things like version control, because each new version would just be added to the edges, for example, if that was the way I was modeling it. But I can also do multiple things at once, which is very hard to do in a relational database. For example, if I want to track two different kinds of time, we call this bitemporal tracking, and I want to track when it was valid, but also when it was recorded. And I could just stack these into my relational model if I want to. But when I'm updating those things, I have to have a really firm grasp of the overall schema before I can do anything, or else I'm not going to get valid data out the other side. And sometimes those update queries, particularly when I'm trying to do things like bitemporal tracking, can end up with some pretty hairy SQL in there. And I'm going to show you sort of some examples of SQL and graph that return the exact same results because it's based on the same data sets, but the data is stored differently. So you're going to see something different in the query itself. Some other advantages I want to go to, and this doesn't just apply to slowly changing dimensions, is that I really should retitle this slide just graph advantages. My attributes can be dynamic. I can add new attributes to my nodes and my relationships between them without breaking the schema. And I don't know how many of you out there on this call, I can't even see you at this point. I'm not used to like doing talks where I can't see people. Ordinarily, I was like, raise your hands and say, like, if you've ever had to adjust your schema for a fundamental change in business logic. And oftentimes what happens is that results in a major development change. And everybody has to go along with it. And all of your front end stuff still has to work. And now, yes, there are tools like object relational models, what we call ORM systems, and tools like Alembic and things like that that can make doing migrations from one to the other fairly transparent. But you still have this idea of you're bound to the schema in a relational database that you just don't have in a graph world. Now, okay, do you want to build a system that you've not thought about the schema at all? Probably not. But we do have this ability to have a much more flexible schema. And also, I would say, if you're in an environment that's sort of in proof of concept mode and you're in maybe R&D mode where you want to try something out, super easy to create new relationships, give them some attributes that you want to test out how they make the data work and what the queries look like, and put it in, test it. It didn't work, just delete it. No changes to the UI. The UI functions exactly the same. And this is a really valuable thing about graph databases, is this ability to add things and not having to restructure your data that's already in there. Now, there are types of changes you could make that would be a little more destructive. If I was doing some decomposition, for example, I said, here's an element and it actually represents two separate nodes. And I want to break this one node into two and define a relationship between them. Okay, that is going to change your UI, is going to change your structure a little bit. You don't get away from that. There's no sort of easy, always ability to change schema without breaking anybody downstream from you. But I would say that in my projects that involved graph databases, I was able to demonstrate concepts way faster because of this flexibility between what my schema is and how I was delivering it to them. And also my ability to talk about it and say, hey, look at what I'm doing here. This one thing explodes out into 5 things that connect to it, and here's how they connect to it. And the tools, such as Memgraph, also give you some really great ways to explore your data in that way. I can say, show me a blue line between all the things that are connected in a certain way. And I don't think I'm going to do that in this particular demo, but if someone wants to see that, just hit me up. I'm happy to show that to you. So how do we evaluate our choices, though? And I don't know how many of you are relational database people. And so I'm going to go through this pretty quickly, but I just want to highlight a couple of things that we use to evaluate how complex a particular process is in the data world. A very common one is what we call big O. And the O stands for Ordnung, which is a great German word, which means order. And I forget the name of the guy that invented this, but these different types of complexities represent from the easiest. This query will execute in a constant time. This one will grow over time. This one will grow logarithmically. This one will grow linear. And then we have some variables that we want to plug into this when you're evaluating complexity. For example, how large is my table? How large is the table I'm joining it to? How deep am I having to look into it? Like, am I having to look, for example, not just at the friends of friends, but the friends of friends of friends, typical sort of social media kind of queries. How large is my result set? How wide is my data? And so, excuse me. In a SQL database, this is a fairly common thing to do. So users and friendships, right? So I'm going to create a table of users. I'm going to create some friendships. And you notice that I have this, this ID here, which is going to this user ID is going to represent a relationship between users. And I can already see people who understand how SQL works, that you kind of put your head in your hands here because, okay, if I only have one friend and they're only one hop away from me, it's just a friend of me. This is pretty simple, and SQL can do that fairly well. But what if I want my friends of my friends, or I want the friends of my mutual friends, or I want their friends? If you've ever had to write a recursive relationship in SQL, you know that it does not scale. It has very high big O complexity. And every time I add either width, result set size, intermediate stuff, the query slows down to the point where once you get 4, 5, maybe 6 layers deep, the queries become almost unusable, even from what we're looking at here, which is a very simple structure, just users and their friendships. So how would I find mutual friends in a SQL example? I could do a query like this. I can say, select me the friend from here, where user ID equals 1, and just intersect it from the friend ID, where user ID equals 2. And this is going to give me the intersection of those two tables, and it'll say, this matches both of them. And that'll give me my mutual friends. The problem with this is, though, let's take a look at what the SQL is actually having to do there. First, I have to scan the data to find the user ID equals 1. And then I have another subquery, which is going to what we call materialize set 2 for user ID equals 2. Then I have to sort and hash both sets, find the intersection of them, and make a set 3. And then I might have to deduplicate it. And so do this join back and deduplicate it. And so you can see this time complexity due to set operations goes up very high. And as your network density increases, this stops scaling very, very quickly. So let's take a look at how this happens in a graph. In a graph, I create my model. Here's Alice, here's Bob, and here's Charlie. And I'm going to just create some friends, basically, in my data here. Create some relationships between them. Create some, again, these relationships between the nodes. And then how do I find friends in a query in a graph database? 2 lines of code. I think I've seen this as 3, but it's really 2 lines of code, because in a graph database, I'm not selecting against a table. What I'm doing is I'm matching a pattern. This person is friends with this person. It's a mutual because this person is friends with this person over here. You can see it's doing the same thing as the relational query has to do, but it's doing it in a graph. And so it's looking for this pattern of friends, friends with, friends, friends with, and the mutual ones between them. And what happens is, if you look at how this executes, and it happens very, very fast. It has to do less things. It has to do less looking for data because it doesn't have to look across everything. It's merely looking at the things you told it to. And I think that this is something to remember when you're looking at graph queries versus SQL queries is you don't often in graph want to look across everybody in the entire graph for the same thing because you're looking for patterns. If that's what you're doing, you're always looking across the entire graph for the same things, you might be better suited with a relational database. And I'll talk about some of these things a little bit at the end there. I'm running up on 30 minutes here. God, I talk a lot. It's okay. So to find mutual friends, it's much, much easier in a graph database because I have the structure of my data, that is the architecture supports doing this much faster. Now there is indexing in a graph database. And so it can do the sort of the matching piece also just as fast as a relational database. It just has to do a lot less to return the result set. So, but let's add some hops in there. right? Let's say I want to go from friends of friends to friends of friends of friends. Well, sure, you could do that in SQL, but take a look at what happens here, right? It becomes very difficult. For example, the optimizer may not know what to do. The optimizer is the piece of code that actually tells it what to do on the disk, basically, and it may not know what to do. And unless you get your indexing exactly right, it can turn up with horrible, horrible queries. You can end up with like what we call a Cartesian product, where you multiplied everything in the database by everything else in the database. And because it has to match on this stuff, what it has to do in those intermediate tables where it's doing deduplication and stuff like that is massively huge sometimes. And so it doesn't know what to do. And it can do things in many different ways, which is not good for a database query. And it's hard to estimate the impact of your query. Whereas in a graph database, take a look at this. I say, match this path of this user with ID, and they're friends with, and I just say times 3 or *3. That means go 3 levels deep to this user ID and return distinct the mutual friends that match that. That is a way, way better performing query than this SQL here. And I have some examples actually in my demo I'm going to get to in just 1 second here. I'm going to try and run through these other things here. The last example I want to show you from SQL to graph is recommendations. And recommendations are a very common use case. I think we all sort of know that. Like, how do I suggest things for people? The noise in the background is my cat meowing. It's not me. So in this particular case, what I'm trying to look at is how can I recommend something to someone? Who would I recommend to someone who they're not already connected to, for example? Who would I recommend a friend to, right? Well, you can do this with SQL, pretty simple. But every single join you need to do, every single layer of depth you want to add to this query multiplies the result set that it needs to filter. Secondarily, you might have to do a not in so that you don't repeat the person who's making the query, who you first start relating the query to. And so this not in, if you're any sort of a SQL person, it's like kryptonite. It slows down every possible query because it has to look across everything to figure that out. And again, it makes, again, just like the other example, makes very large intermediate tables, and the performance drops very dramatically. In a graph, again, way easier, right? Because I have a pattern that represents a friend, which says, hey, this is Alice who's friends with people, but it's not someone she's already connected to. And I just want to return that potential name and the friend name, where they came from. So much easier. So with regards to recommendations, you get this ability to talk about it much easier. If I show you a graph query and you understand sort of the syntax of it, they become much clearer what you're trying to do, as opposed to SQL where you're going, what am I joining to here? Why am I joining to that? Is that a recursive query? Is that running like on an intermediate table? It's very, very messy in the SQL world. And in graph, you don't have this concept of sort of intermediate results, because what I'm doing is, instead of saying, grab this over here, mash them up together, and then give me something out, I'm saying, no, start here, walk over to that other relationship. I call it putting stuff in your backpack along the way where it matches. And then when you get there, tell me how many things matched. And that's a much faster way to get to results than having to look across all your data all the time to get that content. And I have 2 more slides here, and then I'm going to do a really quick demo, and you'll see some cool stuff. So there is often a use case, though, for both. That is a hybrid architecture where I have relational databases and graph databases. And that's not a bad thing. Relational databases, I still do a lot of them on a daily basis. I still do a lot of graph databases on a daily basis, and understanding what they're good for. For example, if I'm doing with highly structured data in my source, and it needs to be highly structured and transactional. Relational databases do that very well. And if my metrics, my rollups, my aggregations are, if I have reporting tools already on top of them, that tends to work much better with relational. But if the relationships themselves in the data are the important things, social networks, recommendation engines, where your output is the relationship, right? Graph excels at that. If I have highly hierarchical structures, I don't know if anybody here has ever tried to build a hierarchical database where I have like an object model or something like that in a relational database. Okay, hot tip, there's a really cool book called SQL for Smarties that tells you how to do it well. But it's very hard. It's very hard to maintain. It's very hard to explain, and it's very schema bound. If I build out like a tree structure in a relational database, it's very hard to explain to people what I'm doing sometimes. They just have to trust me sometimes, which they don't always. And if your traversals of your data, that is what you're looking for in these relationships, is things like a network analysis or fraud. Example of fraud. I have a whole demo about fraud that I've done. I'm happy to do it again sometime if you want me to. About where you're looking for sort of, oh, this person's related to this person by this kind of relationship. Maybe it's address, and this person's related to this transaction over here by what credit card they used, and someone else lives at that address too. Would you want to check that other person's transactions for fraud also? Sort of a community type thing. And those kinds of queries are super easy because they're built into graph architecture to do those kinds of things. And of course, anything where your relationships are highly evolving. That is where it's not sort of fixed in stone what you're doing. You're doing R&D work. You're doing sort of experimental proof of concept type stuff. Graph databases are so much easier to play with and so much more fun, to be honest, because you can do things very, very fast that don't involve going back into my database, changing an attribute. Oh, I missed, it's not a date, it's a string, blah, blah, blah. Breaks everything. No, you can just change it dynamically and rerun your queries. So that's really cool. But I will say that there are some cool patterns around hybrid architecture, and a lot of it is around messaging where you're trying to send things to both. And I already, when I started writing up this presentation, I said, I'm not going to go do a deep dive on this, but I think that might be my next proposed talk to my friends at Memgraph, that I do something about hybrid architecture patterns. Okay, so that's the end of my slides. Before I go into any my very quick demo, does anybody want to ask any questions or have any comments? I'm not sure how I bring people up. Is there like a hand raising feature, or they just want to put it in the chat?
Users can put their questions in the chat, and then we can answer all of those at the end if there are any. Super. So far, I can see, yeah, that there are no questions. Oh, we have one in the Q&A. Okay, Super. Satya has a question. Okay, so why don't I? Satya. Yeah, you can just type it in chat. Why don't I go through my demo really quick, and you guys can think of your questions, and then I'll save some time for Q&A. That sounds good. I'm going to share a different screen here now. Just give me 1 second. Too many windows open. This is what happens when you have like a million monitors too. It's like everything becomes sort of, okay, that one there. Okay. Share, present, screen, window. Okay. So this is a little demo I put together. If anybody wants to know the details of the demo building process, happy to talk about that sometime. But what I did was I created two different data sets, two similar data sets where the data in them match, but one was in a graph model and one is in a relational model. And it's the same model that I've been using in this example about friends and their relationships. So I don't need to show you the models because it's the same thing that we've been talking about throughout this demonstration. So what you're looking at here is, and this is
This is actually a live demo. This is actually querying a local instance of Postgres and a local instance of Memgraph running in Docker containers on my Mac here. So what I'm checking here is find me all the mutual friends between Alice and Bob. And if I execute the query, of course, do this one first and then this one. Come on, don't let me down. There you go. I'm using a tool called Streamlit, which has kind of weird state session management. Sometimes I have to click things several times to get results to show up. But you notice that the mutual friend shows up the same between the two patterns, but the queries are radically different and will scale radically differently too. This query here is just to return that one row. I'm having to do this intersection here, and I have some joins in here. And sure, while this is running with 2 or 3 records in a very small schema, they both perform very, very well. But imagine scaling this up to millions of rows in these tables, and you will see a huge difference between them. And of course, being able to explain to someone that you're talking to, whether it's your end users or your coworkers or something like that, about what you're building is so much easier in a graph database. I can say, look, here's the pattern I'm looking for. And I want to make sure that Alice and does not equal Bob, and they're mutual friends, and they match, and return me a distinct list. All of this happens in a very semantic sort of way, so you can actually see what it's doing. If I go to a more, if I just want to look at who Alice's friends are, this is a very simple example, right? Show me just who Alice's friends are. There's her friends. And the same thing happens here. And of course, it's not wanting to show me all my data. Thank you. It returns 4 rows. It's the same 4 rows. I don't know why it's not displaying on the screen, but we'll just have to live with that. If I want to do recommendations, remember this recommendation query where I want to say, who would I recommend that you know that you don't already know, right? There's my Postgres query results, 3 rows. I'm hoping it's going to show them all here. There we go. The same 3 people, but it's much easier to describe to somebody what I'm doing and much easier to visualize what I'm doing in the data when you're using a graph. And another one, degrees of separation. How far away am I from someone else in my network, right? How many, we call it hops away from someone am I? So here, execute this one first and then this one. There we go. So this tells me that I'm 1 hop away from Bob. And of course, this is using Alice as the starting point, I think. And I'm 1 hop away from Charlie Brown. I'm 1 hop away from Diana. I'm 2 hops away from Eve. You see the results are exactly the same. What you notice is the query way, way simpler, and it's going to scale much, much higher when you start looking at sort of that those ordinal complexity values that multiply up as your rows increase. And the last one I'm going to show you, I think I'll show you bidirectional relationships. That is, am I a friend with someone, but they're also a friend with me? This is the, oh, sorry, that's degrees of separation. Got to change this here. Bidirectional. Returns 13 rows. And I think this will show me the same, yeah, same 13 rows here, right? This tells me that Alice is friends with Bob, but Bob is also friends with Alice. But the query that you're running between the two to get to that piece of information is way more complex on the SQL side. And it's a very, very simple thing to do in a graph database, because I've made the relationship that I'm looking for a part of my data, as opposed to just being something I have to infer from looking at my data and the relationships between them. So those are just a couple of examples of things you can do in a, just one more here. This is Bob's friends. Examples of things you can do in both relational and graph databases, but why the graph is so much more superior. And I'm going to stop sharing now. And I was talking earlier, I will share this demo if anybody wants to take a look at it themselves. It uses Streamlit. I'll probably post on like a just Streamlit distribution site, but it's all written in Python, pretty simple stuff. Bill, you'd love to hear something about hybrid. I'll pass that over to the Memgraph team if they want me to do a talk sometime about hybrid architecture. I think that'd be really cool and show like data streaming with Kafka or something between them. Totally cool. Would love to do.
Yeah.
Yeah.
I guess we have to organize something pretty soon, so stay tuned.
Yeah, stay tuned. Yeah. Any limitation for the amount of data a graph database can handle? Obviously, there's limitations, but the limitations that I found are way, way higher scalability in the same data sets. Now, there are some data sets which are going to work scalable. I mean, I've built multi-petabyte data warehouses, so that's not like it's not just about the volume side; it's about your ability to query out of it. And we talk about unstructured data a lot too, sort of like how much unstructured data can I store? And I kind of push back on that a little bit. I would say that there's no such thing as unstructured data. And that's my provocative statement for the day, because there's unmodeled data. That is, it's data I don't understand how it's working, and I need to get it out. Maybe some of you have dealt with what they call data lakes. I think they're horrible. I always tell people that data lakes is where data goes to die. And because you can put a lot of interesting things into it, but it's very hard to get out. It's very hard to get out of it good intelligence without really complex queries. And Graph sort of helps you there because it says, if I'm going to put something in, I at least have to understand the nodes and their relationships. I can't just dump raw data into it and do nothing with it. You still need architecture. You still need to do things right. But I think that in Graph, your ability to talk about those architectures is much more useful in this regard. So I would say if you look at LinkedIn, if you look at Facebook, all of these high-performant social network sites all have graphs behind them. I don't know which one, can't speak to that, but I'm certain they all have graphs behind them because Relational just can't do those kind of queries in the kind of speed with what you can do. So you can imagine, billions and billions of nodes and being able to find the relationships between people in them for like fraud detection and stuff like that very, very quickly. So
yeah, we have a similar question from Satya. He's wondering what kind of volumes can graph databases handle?
So in the real world, I would say graph databases don't have a problem with millions of nodes. I mean, in fact, that's actually rather trivial to a graph database. But I'm not bashing relational databases. Relational databases can have millions of rows too. Time series databases like Elastic and stuff like that can have billions of rows too flowing into them. I've done millions of rows per second actually in streaming data applications. So it's not just about the amount of data that it can handle. It's about how you structure it to get something meaningful out of it. And Graph is a really powerful insight engine for getting that out of it in a way that a relational person, let's say you're loading, billions of rows into a multi-petabyte data warehouse. Well, you're probably using what we call MPP architecture, like multiple parallel processing, where you have different CPUs all sort of flowing the data at the same time. You have to know a lot about that to get results quickly. It's not impossible. I've built multi-petabyte data warehouses that still have sub-second response time because of how the data is structured. And so, but you need to think about it. And whereas in Graph, you have a lot more flexibility there, particularly flexibility where you need that high performance.
Yeah, and especially in Memgraph. Memgraph is in-memory graph database, and then you're not limited by the amount of your data, you're only limited by the amount of your RAM available. So once you have enough RAM, you can store as much data as you'd like in your graph database. Of course, we don't measure like data in amounts of nodes and relationships because there's much more to it, like properties and if there are string properties or not. So yeah, your only limit is the amount of RAM available.
And you don't lose the need for being able to architect something correctly. I think that's a really important point, whether it's relational, time series, document databases. I mean, how many of you have seen really ugly document databases, for example? If you ever use MongoDB or something like that, they can end up with really crazy data in them that's really important to the company, but nobody knows how to get it out, And so data architecture is still a very valuable skill. I'm happy to be a data architect because I don't think I'm going to be replaced by AI anytime soon, particularly for that reason. Being able to come up with good architecture is still a holistic exercise, that requires creativity and thought. So,
Yeah. We also have a question. Can you send the link to your pro demo? Do you maybe have that available?
Yeah, I don't have it published yet. So what I will do is, do you have everybody's email, Matea? If I send it to you once I publish it, can you share it?
No, unfortunately not. But what we can do is we can put a link with this. This recording will be publicly available later,
Yeah,
so we
that's
can
probably a
have a
good place
link
to
in the
start. Yeah.
description.
Let me put
Yeah.
my email address in there again too, so you can write to me, and I will and just say, hey, let me know when you when you publish that up. So,
Yeah, that works. And one more question. So relational database have evolved over the last 40 plus years and have a maturity in terms of mission critical applications. Our graph database is there in terms of volumes, availability, scalability, concurrency, security, and performance.
I would say absolutely. I think part of the problem is graph databases don't get a lot of the attention that sometimes relational databases get, but they're all there. It's not like the world isn't using them in the same way, and they can still be deployed using containers. They can be you can do all the same security type things. It's a slightly different mindset, though. It's slightly I hate to use sort of esoteric terms, but it's a slightly more creative mindset that applies. But all the hardening that you need to do for deployment in the real world exists in Graph also. It's not like they're just it's not like Jupyter notebooks on the desktop or something like that. It's a much more hardened environment in that space for being able to deploy because people are using them. Pharmaceutical companies, for example, are using them for the example that I had was sort of a document generation use case, and at scale, millions and millions of nodes, millions and millions of relationships between them, and doing all this in a highly secure, sometimes in a highly secure multi-tenant way also. So the kinds of things that we take into the sort of the DevOps and the deployment world of relational databases also exists in Graph, definitely, and being able to run mission critical stuff on it, piece of cake. He says, as the architect.
Yeah. Great answer. I think that's it from the questions. As far as I can tell, hopefully I haven't missed any. But yeah, thank you so much, Frank. This was a great presentation, and it was really interesting to see like real world examples of shifting the mindset from relational to graph model and how much simpler it actually is. Like not only the structure and the connections, but also the queries as well, and how quickly things can get complicated in relational database. So yeah, this is really interesting for me and hopefully for everybody else as well. Yep. And I think that's it. We don't have any other questions. Thank you again, Frank, for the presentation. It was really useful, and I hope everybody enjoyed as well. And thank you, everybody, for your time, and I hope you have a great rest of the day, and I see you on the next community call.
Thank you so much. Look forward to talking to you later. I'm on LinkedIn, and just find me anywhere. I'm happy to chat about this stuff anytime.
Awesome. Bye, everyone.